Introduced definite integrals and what they are. So here we'll be talking about how these definite integrals relate to area. We'll also talk about integration as accumulation, which we've spoken of before, and our example of that in this section will specifically be something called revenue streams. So, definite integrals as area. So let's recall from 5.3 the fundamental theorem of calculus, which says that if f of x is continuous and capital F is an antiderivative, then the integral from a to b of little f of x is capital F of b minus capital F of a. And this definite integral from the fundamental theorem of calculus gives us the area under the curve. Right? When I say that, what I mean is the area of the region, here shaded in orange, between the graph of f of x and the x-axis from x equals a to x equals b. Right, so I'll say that again. This definite integral from a to b of little f of x gives us the area between the graph of f of x and the x-axis from x equals a to x equals b. That's how we can interpret definite integrals as area. So let's look at an example here. I'm going to give us a graph. It's a graph of f of x. And I want to use a definite integral to express the area of this shaded region. Right, so recall from the last slide that the definite integral will give you the area between the graph and the x-axis between a and b. So here, if we want the area from x equals 1 to x equals 6, that's under the graph of f of x, between the graph of f of x and the x-axis, we can write that as the definite integral starting at 1 all the way to 6 of this function, whatever it is, dx. Right? So the definite integral from 1 to 6 will give us the area between the graph and the x-axis from x equals 1 to x equals 6. Right here, shaded blue. Right? So what is that? Well, that's the area between the graph and the x-axis starting at 4 and ending at 5. So that'll be the definite integral from 4 to 5 of f of x. And that'll give us the area of that shaded blue region. Here I've got the exact same graph, but this time I want to express the area that's shaded red. Right? So what's different about this blue section and this red section? Right, well, the blue section, that's underneath the graph, between the graph and the x-axis. And we've already said that that's going to be given by just that definite integral. This red section is sort of above the graph. Right? It's still between the x-axis and the graph of f of x, but the graph of f of x is below the x-axis over here. And so the way that's going to show up with a definite integral is by a negative sign. So what do I mean by that? Well, the area of that red region is still given by the definite integral, so starting at 2 and ending at 4, so from 2 to 4 of f of x. But because the graph is below the x-axis from 2 to 4, this integral is going to spit out a negative number. And so since we don't want area to be negative, if I want the actual area of that region shaded red, I need to force it to be positive by sticking a negative sign out in the front of this definite integral. So the definite integral that will give me the area of that shaded region is still the definite integral from 2 to 4 of f of x, but because the graph is below the x-axis the whole time, I need to put a negative sign out front to force that definite integral to then be a positive number, which will give me the area. If I don't have this negative sign, I'll have a negative number, and it still basically gives me that area, but it gives it to me as a negative number. So this negative sign in the front of the definite integral will just undo that negative number, that negative sign, and turn my negative number into a positive number. It's combined. Well, I'm just going to take the two definite integrals from the last slide. So what is that? Well, remember, for this red region, because it's completely below the x-axis there, I need to take negative the integral from 2 to 4 of f of x, and that will give me the area of that red region as a positive number. And then I want to add whatever's going to give me the area of the blue region, which, remember, was the integral starting at 4 and ending at 5 of f of x. So these two integrals, this sum, whoops, that was a bad box, but that's okay. That will give me the area of the blue part plus the area of the red part. But notice that that's not the same thing as the integral from 2 to 5, where we go all the way starting at 2 to ending at 5 of f of x, right? Because we took the 2 to 4 part and made it negative. So what would the definite integral from 2 to 5 represent? Well, instead of giving me this area plus this area, the integral from 2 to 5 would give me something called the net area. And that will take the area of the part that's above the x-axis and count it as a positive number, and the area of the part that's below the x-axis and count it as a negative number, and just add that up. And that's what the net area is the stuff above the x-axis gets counted as positive, and the area below the x-axis gets counted as negative. And if you just take the derivative, or I'm sorry, the antiderivative, the definite integral from 2 to 5, you'll get that net area. And so that's an important distinction between the total area, like this, where you have to account for which part is negative, and the net area, where it's going to add the stuff above as a positive number and then subtract off the area below. Right, so this net area can be a negative number. For example, looking at this graph, it probably would be, and we'll get to an example of that in a few slides. And if that is a negative number for that net area, all that means is that there's more area below the x-axis than there is above. Right, so I say this integral probably would be negative because it looks like the red area is greater than the area of that blue section. And so that net area gives us the area between the graph and the x-axis, right? When the graph is below the x-axis, that area is counted as negative. And when the graph is above the x-axis, that area is counted as positive. And so if it's strictly above, then this integral will give the entire area because there was nothing to be taken away. And the integral will be positive. If it's strictly below, then it would give us the entire area, but as a negative number. And if it's above and below, it gives the net area, which is the region above minus that area of the region below. All right, so let's look at an example here. I've got a graph on the right side, and I'm asking, would you expect these integrals given to be positive or negative? Right, so I'm going to give you an integral, for example, the integral from -1 to 0, and say, do you think it'll be positive or negative? Well, remember, the integral from -1 to 0 is going to give us the area from x equals -1 to x equals 0, which I'll shade in extra red here. And so do you think that'll be positive or negative? Well, let's see. That entire region is below the x-axis. So we would say that this is probably, and it should be, negative for that integral, because that entire region is below the x-axis. How about from 0.5 to 1.5? So let's say that's something like, here's 0.5, here's 1.5. And that part of the graph is completely above the x-axis. And so when we take that definite integral, we expect it to be a positive number. Now, if we look at the definite integral from -1 and running all the way to 2, remember that will give us the net area. Right, so what I have shaded in blue would be counted as positive area, and what I have poorly shaded in red would be counted as negative area. And so if we're trying to determine if this is positive or negative, we would look at this and see which one does it look like there's more of. And so since it looks like there's more negative area, more red shading than blue shading, we would guess that and ask you to find the area of the region bounded by this function and two x values. Right? In this case, x equals 4 and x equals 6. Right? So let's graph this guy first and see what it looks like. Right? Because if it's above the x-axis there, then we know that we can just take a positive number. And if it's below the x-axis, then we need to make this thing negative. So this graph is f of x is x squared minus 10. So what does that look like? Well, it looks something like this. And you can double check this on your calculator, of course. And let's say 4 is right here and 6 is right here. Right, so the area of the region bounded by this graph and the two lines x equals 4, x equals 6, or the three lines, and also the x-axis, is this area right here. Right, so anytime we're asked to find the area of the region bounded by the function, two x values, in this case 4 and 6, and the x-axis, we have to look at the graph and check and see if the graph is entirely above or entirely below the x-axis to see if we need to take a positive or negative integral. In this case, since it's completely above, that area is going to be given by the definite integral from 4 to 6 of f of x. And we don't need to make it negative because it's completely above the x-axis. All right, so what is this definite integral? Well, it's the integral from 4 to 6 of x squared minus 10 dx. Right, and I'm assuming that you guys are comfortable with taking these definite integrals from 5.3.
Sorry. Excuse me.
That's all right.
Siempre batallo bastante, pastorcita. Okay. Sorry. Gracias, pastora. Aquí hay que limpiar, entonces hay que limpiar la refrigerador y el de este. Okay.
Thank you.
You're welcome.
So we're going to do the same steps as before. So let's first look at the graph of this function and determine if it's completely above or below the x-axis. Or perhaps partially above, partially below. So when we graph this, e to the minus x plus 2, it looks something like this with the horizontal asymptote at the height 2. All right, so something like that. And so if we go from 1 to 5, that graph is completely above the x-axis. And so we are asked to determine this area here between the graph and x equals 1 and x equals 5 and the x-axis. So since the graph is completely above the x-axis, we're going to take the definite integral and not make it negative, just leave it as is, starting at 1, ending at 5 of our function, e to the minus x plus 2 dx. And this definite integral is going to require a u substitution. So what do we want u to be? Well, we have e to the something, so let's let u be that entire exponent, minus x plus 2. All right, now remember, we want to substitute something in 4 dx that has a du in it. So we take the derivative of this equation. On the left side, the derivative of u with respect to x is du dx. On the right side, the derivative of minus x plus 2 with respect to x is negative 1. So solving for dx, you get dx is negative du. So now we're going to plug in for minus x plus 2, we'll plug in a u, and for dx, we'll plug in a minus du. Right, so we're going to leave our bounds, this 1 and 5, the same. Right? And technically this is cheating because that's supposed to be x going from 1 to 5, but that's okay. Just leave it from 1 to 5, and we'll just worry about taking the antiderivative first, and then we'll worry about the 1 and the 5. Right? So what's the antiderivative is what we're working on here. So we get e to the u, and then a negative du. So that negative comes out, and this is negative, the definite integral from 1 to 5 of e to the u du. So now we can do this, and we get the antiderivative of e to the u with respect to u is just e to the u. So there's our antiderivative, and this negative sign comes along for the ride. And then we're still doing the definite integral, so we're going to evaluate that from x equals 1 to x equals 5. All right, so that 1 and 5 are what x is supposed to be. So we can't plug those in until we substitute back in our x's, and so let's do that. All right, this is the same step that we would normally do for an indefinite integral with u substitution. And so we substitute back in, and we're still evaluating from 1 to 5. All right, so we use u substitution to go from here to this antiderivative, and we just left the 1 and the 5 and brought them along for the ride. Once we actually get to the antiderivative with the x plugged back in, now we can plug in our 5 and plug in our 1 and take the difference. So what is that? Well, when we plug in 5, we get minus e to the negative 3. And then we're going to subtract. And when we plug in 1, we get minus e to the 1. And so that's minus e to the negative 3 plus e. And you don't have to approximate that as a decimal. Just box that answer. Remember, e is just a number, so e to the negative 3 is just a number. When you add and subtract, that's still just some number. And that is the area between the graph and x equals 1, x equals 5, and the x-axis. So to recap, we were given a definite integral, or we have a definite integral in order to find this area. We noticed we're going to have to use u substitution, so we do our u substitution just like normal and bring the 1 and 5 along for the ride until this step. And in this step, that was where we had substituted back in what u was in terms of x. Once we have the x's back in there, we can then plug in like we have been doing. All right, so now let's move on to our example for integration as accumulation for this section, and that was something called revenue streams. Right, so revenue streams, what is that? Well, what it is if you are having money flowing in, right? Revenue is continuously coming in. Maybe you've got an apartment you're renting out or something like that, or interest on an investment, whatever it may be. You have to have money continuously coming in to your account or whatever it is, right? So your revenue continuously coming in. Then we can calculate how that revenue is accumulating using a definite integral. Right? And so that continuous revenue, the money coming in continuously, is called a revenue stream, and it's given as a function r of t. So if I say r of t is a revenue stream, or you've got money continuously coming in at the rate of r of t, that's the same thing, then I'm going to ask what is the total revenue that's accumulated, or what's the total money that you've gained, something along those lines, and you can find that by finding the definite integral from time A to time B of your revenue stream. So if you have a revenue stream and you want to know what is the accumulated revenue from time A to time B, you're going to take the definite integral from A to B of your revenue stream function. So let's look at an example of that. It says Sully invested money in stocks, which he now expects to produce a revenue stream over the next 10 years, modeled by r of t is 1,000 times the square root of 2t plus 5. So here t is the number of years, where t equals 0 is right now, t equals 5 would be 5 years from now, etc. Right, so this says find the total revenue generated by the revenue stream over the 10-year period. All right, so this function spits out the rate that the money is flowing in at time t. If I want the total revenue, I need to integrate that revenue rate or that revenue stream. So I want to find the integral of r of t, and that's going to give me my total revenue. I'm going to take the integral of the revenue stream to find the total revenue. Over the 10-year period means that I want to start right now at time 0 and end at year 10. And that definite integral will give me the accumulation of my revenue over this 10-year period. So let's plug in r of t. This is the integral from 0 to 10 of 1,000 times the square root of 2t plus 5 dt. And again, to take this antiderivative, I will have to use a u substitution. So what do I want u to be? Well, I've got a square root of a bunch of stuff, so I'm going to let u be all the stuff inside the square root. That's 2t plus 5. So I'm going to plug u in for 2t plus 5 here. And I also want to plug in something for dt there. So I'm going to take the derivative of this equation with respect to this variable t. On the left side, I get du dt. And on the right side, the derivative of 2t plus 5 with respect to t is 2. So solving for dt, you get dt equals du over 2. And so we're going to plug in for dt, du over 2, and plug in for 2t plus 5, u. So this is now the definite integral. Again, this 0 and 10 are just going to come along for the ride for now. The thousands also hanging out, doesn't change. And I've got the square root of u now times du over 2. All right, so I'm going to rewrite this to help us take this derivative. 1,000 over 2 is 500, and that can come out of that integral. Remember, we can always pull those constants out. The 0 and the 10 still come along for the ride, and square root of u is u to the 1/2. So we have u to the 1/2 du. That's what we're taking the antiderivative of. All right, so I start by taking the antiderivative with respect to u there, and I get, well, the 500 comes along for the ride. U to the 1/2 becomes u to the 1/2 plus 1, which is 3/2. divided by that new exponent, 3/2. And then I'm going to evaluate this from x equals 0 to x equals 10. So I'm going to leave that there along for the ride, the 0 and 10. And my last step here is going to be, oops, sorry, not x equals, but t equals. T is our variable here. The last step is going to be to plug in our u equals 2t plus 5. That 500 divided by 3/2 can be simplified to 1,000 thirds. Right, so double check that you can get that. So that was this 500 over 3 over 2. You multiply by the reciprocal of 3 over 2, which is 2/3. 500 times 2/3 is just 1,000 thirds. And now, instead of u, we'll plug in 2t plus 5 to the 3/2. And that's what we want to evaluate from t equals 0 to t equals 10. So you're going to plug in 10 first, and you can double check what I got. But I got, when you plugged in 10, 125,000 thirds. So 125,000 over 3. And then when we plug in 0, we're going to subtract, and then I rounded this a little bit. It's something like 3726.8 or so. And then the number you get when you do that subtraction, this is in dollars. This is our accumulated revenue. And so I'll just round to the nearest dollar here. It was 37,940. So by integrating the definite integral of the revenue stream from time 0 to time 10, I'm going to get my accumulated revenue over that 10-year period. And I ended up accumulating $37,940. Definite integrals and area and revenue streams. There's your homework, and there is Sully. Dog.